Thank you, David. All right, so welcome everybody. Today, our first seminar is going to be given by Victor Teng. Victor received his master's degree in environmental sciences from the University of Hawaii, and then came here. I think he worked for a while in GIS type work in Wisconsin, and then came here, is it 5 years ago now? 4 years ago.
4 years ago.
Yeah, it's 4 years ago to start a PhD in water resource science. And he's decided he want to concentrate on hydrology. And a particular area of interest that he had in hydrology was being able to forecast floods. Of course, a big issue because of the economic and human damage that occurs as a result of flooding. And I think maybe part of the reason he got this idea was because of work that he was doing, or connection in work, the project we had where we're using a satellite for monitoring water storage, gravity satellite, which is put up by NASA. And there's been some work where people have tried to use that information as an index for being able to forecast floods months and months ahead of time. So Victor has taken this up and has, with the idea of using satellite data and that kind of thing, he's not directly using satellite data, but using a model to generate flow data for rivers, and then trying to use a artificial intelligence, that is a machine learning algorithm, to be able to emulate the flows. And what he's going to be showing today is that including a state variable such as water storage, which we could measure with a satellite, for instance, improves the emulation capability of the machine learning model. So with that, I'll let Victor get started.
Yeah.
You should record it also.
Oh,
It is recording.
okay. Thank you, Dr. Niebuhr. Hello, the WRS students.
You can probably move that window that is on the middle, move it to the side.
Here?
Yeah.
Thank you. And thank you for being here on a Friday afternoon. My name is Victor Teng, the PhD candidate of Water Resource Science graduate program. Today, I'm going to present my work, our long short-term memory model simulation of watershed discharge improve when water storage is included as input. The case study at Rum River Watershed, Minnesota. This slideshow consists of two parts. The first part will be my presentation, in which I'll explain the background, the objectives, the process, the result, and the discussion of the result. And the second part will be the question Q&A session. Before I continue, I want to ask you folks a question. Why water storage matters? Water storage matters because flooding matters. Water storage matters because the storage discharge relation matters. Flooding is one of the most devastating natural disasters of the United States and the world. From 1980 to 2022, there has already been 36 flood events whose damage has exceeded $1 billion. Just this summer alone, we already have different floods across the United States, including Missouri, West Virginia, Kentucky, Nevada, Illinois. Also, we should also including Texas or Arizona and California. Just name a few. The severity and the frequency has furthermore, the severity and the frequency of flooding has gradually increased in the last 20 years. Those graphs are the data from the National Weather Service. On the left, it shows that the count of flood has increased in the lab from 1980 to 2022. And the graph on the right shows that except for 1993, the cost of flooding, the cost of damage has increased gradually, except if we just ignore the 1993, which was not an anomaly. Flooding is also a worldwide problem. According to the United Nations analysis, it found out that floods has accounted for 47% of all weather-related disasters from 1995 to 2015. And it has affected 2.3 billion people and directly cost the life of 157,000 people. Here are a few examples of the flooding this year, including the flooding in Australia this winter, also including the South Africa, Brazil, and Pakistan. Therefore, in order to minimize the casualty and the economic damages of flooding, we need to keep flood data and forecasts available and accountable. We have the potential to improve our existing flooding forecasting by understanding the storage-discharge relations. In Dr. Keith Stevens' work, Search for a Holy Grail of Scientific Hydrology, he has stated that a good flood prediction should including knowing pattern of not only rainfall, the characteristic of the watershed, the time step, but also the spatial temporal distribution of the total water storage within a watershed. Currently, the water storage has not been used for predicting the flooding in the United States today. Since 1971, flood was forecasted based on the collected data from the stream flow and stage, rain gauge-based precipitation, snow water equivalent, and the reservoir flows. Water storage will be very difficult to directly monitor. Currently, we have an easy way to monitor the water storage with a satellite image called the GRACE, Gravity Recovery and Climate Experiment. Even though in the past, it already has the capacity of predicting the water storage on both the groundwater and the water surface. And in the past, scientists tried to use it for flood forecasting experimentally, but it was not working. It was not used in the flood prediction today because of its coarse resolution. In order to make the GRACE data usable for future flood forecasting, we have to downscale the GRACE data. Therefore, here comes to the objective of this presentation. It's asking two questions. First, can we improve the accuracy of the stream flow prediction by including total water storage at a watershed? Second, if we can improve the stream flow prediction, can the downscaling of the total water storage improve the stream flow prediction at a local region? This slide shows, in our research, we'll apply the machine learning algorithm for stream flow prediction. Machine learning, according to the Oxford Dictionary, is a type of artificial intelligence in which computer use huge amount of data to learn how to do tasks rather than being programmed to do that. When computer scientists and hydrologists input weather data and hydrological variables to machine learning algorithm, we're training the machine learning algorithm. And then we'll use, after we train the machine learning algorithm with the input data, we will use that for predicting the result. Because of the capacity of machine learning algorithm to capture the large number of data, it has been grown. More and more hydrologists and the computer scientists have used it for predicting the stream flow or doing other type of hydrological works. And this diagram shows you how the traditional hydrological modeling and machine learning algorithm are different. The upper one shows how the traditional hydrological modeling was done. You use the you understand the hydrological process of the stream flow, and then you input the weather data to see the result, and you calibrate it to see how accurate the prediction of the hydrological model be. In the machine learning algorithm, why does that? You will input the weather data, the past stream flow and weather data to train the machine learning algorithm, so that machine learning algorithm will be able to predict the stream flow. Even though it provides a way for the scientists to establish a nonlinear relation between the weather data and the hydrological variable we want to predict, like stream flow. It has a weakness because we will never know whether the result of machine learning will be always accurate according to the geographic and hydrological processes. For example, if you just trust in the machine learning algorithm, you probably will find out the result will not fit the water balance model. So that will always be a challenge for using the machine learning algorithm to predict the stream flow. And my solution of machine learning algorithm weakness is to train the machine learning algorithm with the weather data and the hydrological variable simulated by the hydrological models, so that the machine learning algorithm will learn from the unbiased hydrological data that already include the water balance model, routing, and the geographic processes of the watershed. And this is type of process by using the scientific knowledge to guide the machine learning algorithm is called knowledge guided machine learning. And in the experiment, the machine learning algorithm I'm going to use is called the long short-term memory network. It was used because it has improved from the machine learning algorithm in the past. It can not only learn from the weather data from I input, but it can also include the weather data from the past, maybe one day, a month, or a year. Since the hydrological models, since the total stream flow will also be impacted not only by 1 day or one time period, 1 month, but also like a certain interval, a lot of time. Long short-term memory network has a capacity to include the weather variable in the past and to predict the stream flow. And the model I'm going to use is called Hydrological Simulation Program Fortran. It was first invented in 1980 it would by the EPA. It has been used for modeling the agricultural runoff, sediment erosion, this dissolved oxygen, and the discharge. It overall it simulated the quality of a quantity of a stream flow by using the water balance model and the interconnect and the simulation of the interconnected sub-watershed of the selected site. And with the HSPF is a physically based hydrological model that simulates hydrological variable stored it in each of the smaller watershed, and and then by simulating the connection of different smaller watershed, it will predict how the quality of the quantity of the watershed. In this experiment, we're going to use its function of predicting the total stream flow, the vertical water storage within each of the sub-watershed, and oops, let me see. Yeah. Oh, excuse me. And the spatial distribution of the water storage. So, and yeah, and this show, excuse me. And I want, overall, here is the blueprint of my research. I will first test how the accuracy for the machine learning algorithm by inputting the weather data and outflow simulated by the HSPF to see how accurate it is. And then I'll compare how much improvement if I try to input the water storage as one of the input variable. And I want to see how much improvement there will be with the result by using the machine learning based hydrological model after including storage. So before storage, after storage. And the site I'm going to choose will include Rum River Watershed located at central Minnesota. I chose this site because based on the past project from Dr. Niebuhr, which already have abundant data. And the other side, if I have time to compare, it will be the Wild Rice River, which has a pretty different characteristic from the Wild Rice River watershed. And my experimental design. The experimental design will be that I will compare the accuracy of a stream flow of simulation by training the LSTM network with weather input, including and excluding water storage. And the data I'm going to use for Rum River Watershed will be from 1995 to 2015. And for the Wild Rice River, I'll use from 1995 to 2009. And just for the visualization, here's a better explanation. In the control group A, I will train the LSTM network with total discharge and seven weather input used by the HSPF. And then excluding the total water storage. In the experimental group B, I will train the LSTM network with weather input, total discharge of the watershed, including 1 out of 6 different layers of the water storage, plus the total water storage. So there will be multiple stream flow prediction by including each one of the water storage. By doing so, I want to see which prediction will be the highest by including each one of the water storage. both control and experimental group predicted discharge, and both prediction will be compared to the simulation result from our original result of HSPF. And then we will evaluate the accuracy of the prediction by comparing the HSPF data, total discharge, which is our Q observation, and the prediction, which was the QS. We'll first compare the hydrograph of the prediction of the observed total outflow, the prediction, the prediction without storage, and the prediction with the storage. And then we'll use the NSC test to test the accuracy of prediction. And NSC test will rank from 0 to 1. 0 means the least accurate, 1 means the most accurate. Oh, and the second part is that I would like to downscale. Excuse me. Oh shoot. The second part will be after I'm done with the testing of total water storage, I will test the result of testing, inputting the downscale water storage from HUC 12 to HUC 8. And you will hear the HUC 12 and HUC 8 a lot. And what HUC it is on HUC is the hydrologic unit code, which was a national system delineated by the USGS. HUC 8 means the 8-digit hydrological unit of the watershed. And HUC 12 will be the sub-watershed within the HUC 8 watershed. And since they will have 4 more digits in the watershed, so it was called HUC 12. And this will demonstrate visualize how HUC 10, 8, HUC 10, and HUC 12 look like. And in the second part of the experiment, it will be very similar to the first part, except I'm going to input the I'm going to simulate the isolated outflow from each sub-watershed by inputting the local weather data, local outflow, including and excluding storage. And there will be control group will be the 131 discharge prediction of 131 discharge without water storage. And the experimental group will be the prediction, including the different layer of storage. Again, it's the same total storage and 6 separate storages. And wait, this slide will be wide. It will be similar to the previous the experiment before downscaling it, except I'm going to use the machine learning algorithm to predict the stream flow with and without including water storage. And I'm also going to use a similar way to predicting the accuracy by using the NSC test. And I first will just show you how the NSC value has been improved with a simple map. And then I'm going to use the box chart for showing how the improvement of the 131 watersheds. And the program I'm going to use will be both the HSPF and the LSTM model developed by Kraser, which he has used for monitoring multiple watersheds. And sorry, how much time do I still have? Okay, sure. I think I can slow down a little bit. So here is the first result of a prediction. The first the hydrograph on the left shows the blue one was the result of the observed data from HSPF, and the red hydrograph was the prediction without the storage. And as you can see, the problem is that it has the difficulty of predicting the peak flow of the hydrograph. Again, this one shows the discharge of the total outflow from the Rum River watershed, and it shows that, and without water storage, it cannot predict the peak flow. And the graph on the right shows the result after including the shows the prediction after you include the total water storage. It was shown in the yellow hydrograph. As you can see, I just put the red hydrograph, which means no, the prediction without storage. The yellow one was the prediction with total water storage of the Rum River watershed, and the blue one was the original input data, which was the which was the observed data from the HSPF. And I want you to see the peak. You can obviously see that the accuracy has been increased because it has done better job on predicting the peak flow. And then we can see the NSE coefficient went from 0.05 to 0.67. It was a significant improvement by including a total water storage. And this one will be the result by comparing the result by not only including a total storage, but also including the different layer of the storage. And we find out that the accuracy has increased the most by including the active groundwater. And then the accuracy will be increased the second by including the surface and interflow storage. So it shows that by inputting the different layer of water storage, you can also improve the prediction of the total stream flow in different degrees. And this result, since we still have time, I will just show my second run at the Wild Rice River watershed. It also shows a similar pattern that with if we try to train the machine on LSTM to predict the total stream flow from Wild Rice River without water storage, it will give us the result of the hydrograph shown on the red when our observed data was the blue one from the blue one. And it also shows that it had difficulty of predicting the peak flow of the total water storage. And I tried to do the same thing again by including the total water storage of Wild Rice River, and it shows similar pattern that the total by including the total water storage in the LSTM model, the prediction of the total stream flow has increased from negative 0.14 to 0.27, even though it's not as ideal as a result of Rum River watershed. The result shows improvement, and this graph shows the improvement by including different layer of the total water of the water storage at Wild Rice River watershed. This map shows the overview of the improvement. And what I do is that after I calculate the NSE value of each of the sub watershed, I mark the area with increasing value of the NSC with green, and I mark the area with decreasing NSC with red. And overall, overall, the map shows that the active groundwater, by including the active groundwater storage, interflow storage, and surface storage, it has the best overall improvement of the prediction at Rum River Watershed. Also, you also have a tremendous improvement by just including a total water storage. And I also and this box chart shows the NSE test result of all watersheds. The NSC no S means the result prediction with stream flow prediction without including the water storage. It shows that it didn't have a pretty high average value, but by including the different layer of water storage, you all see that there's some degree of improvement. And among the different layers, by including the active groundwater storage, it has overall the best improvement of the prediction. So at Rum River, overall, in summary, at Rum River Watershed, including the active groundwater storage will improve the prediction of the local stream flow at Rum River Watershed the best. And I also like to show similar result from the Wild Rice River Watershed. It shows a similar pattern that by including the total water storage, it has a significant improvement. But by including active groundwater storage, interflow storage, and surface detention storage, and upper zone storage, you will have the best overall improvement of the prediction at the sub hot 12 watershed level. And the result of the Wild Rice River Watershed is slightly different from the Rum River Watershed. It shows that by including different layer of water storage, it did improve the accuracy of the prediction at the local level. But in contrast to the Rum River Watershed, in Wild Rice River Watershed, by including the surface water storage, it has the best overall improvement of the prediction at Wild Rice River Watershed. So here comes our discussion. So our results overall shows that by including a total water storage, we can by including a total water storage to train the LSTM model, we can significantly improve the existing machine learning based stream flow prediction model. And among different layers of the water storage, we find out that active groundwater, interflow storage, and surface retention storage can improve the prediction of stream flow, both at the HUC A level or the HUC 12 level of the watershed. And since we still have time, I will also have to talk about another thing I observed, which will be the hysteresis of the storage discharge relation. Hysteresis is what is hysteresis? Mathematically, it means the response of the external influence of a double value function. One value will apply when the influence is increasing, and the other apply when the influence is decreasing. So you'll form a loop. Instead of forming a function, you'll form a loop. And such a pattern has to be observed at the water retention curve, as well as the storage discharge relations. if I try to compare, if I try to undo storage discharge relation with the data I had from the experiment we have seen previously, I have observed that the first one is the hysteresis I simulate for the observed data from HSPF, and the next 8 hysteresis was the result from the simulated data, and it shows that the simulation have a difficulty of simulating the higher when the value is higher in the total storage. And we also find out the similar pattern at the Rum River Watershed. So that was our observation. And my next step is that I will have to figure out how to use the how to explain such hysteresis and how to apply such a hysteresis to improve the existing prediction of the for the machine learning based rainfall runoff model. So in conclusion, my experiment shows that the LSTM model can apply storage discharge correlation to improve the stream flow prediction by far. And by vertically disaggregating and spatially downscaling the water storage to the different layers and hot coil watershed, we can improve the we can not only improve the prediction of the stream flow at local level, we can also examine how the spatial distribution of water storage can improve the local stream flow prediction. My next challenge will be to understand storage discharge analysis better so that I can use it to apply such an understanding to improve the downscaling of the water storage and improvement of the local stream flow. Furthermore, I will by understanding how to explain a storage discharge hysteresis in the HSPF, I can apply it to improve the prediction of the both of downscaling water storage, and the prediction of the stream flow with not only the hydrological model is simulated data, but also the data we found from the we monitored. Thank you for your time, and I want to give special thanks to Dr. Niebuhr, Dr. Bruce Wilson, Dr. Olmenson, Dr. Regan, who gave me all the data from the HSPF, Tracy, as well as Francisco and Sean, who have gave me the data and the assistance I needed, as well as the BBE and the CFAN. And mostly, thank you all for being here and being patient to listen. And thank you, David. Yes.
What made you select HSPF for your watershed model?
That is a good question. HSPF was used because it was the most used model for the EPA, and it was the model we used for predicting flooding. So it definitely has certain. Even though I think I have a discussion with Dr. Niebuhr. I think you can double check with me because we do have this discussion in the past, and we found out that HSPF has such a merit because it has been used for predicting flooding for by the EPA for a while. So,
a big reason is that all 88 Hurricane watersheds have been calibrated with HSPF has been calibrated for all watersheds. Through the MPCA support. So then you don't have to worry that your model you know, if you use HSPF for the Rum River, well, at least it's been calibrated for it. I mean, it's not probably the best physically based model, but, you know, we don't really care about having all the, it does the water balance properly. Does it do, you know, will it do as well as the exchange of flow between, you know, fluid between this point and that point as a, you know, physically-based model? I don't know. But, you know, the relations are complex, and the question is, can LSTM capture that?
Do you have any idea about what kind of model do you think will work to?
I guess I'm always curious when people select watershed models for projects, especially you're doing, I think, a really important service to calling attention to storage, which is a huge
Yeah.
issue between the inputs and the outputs, and thinking about where that storage is in the watershed and how deep into the ground the watershed kind of goes and what the calibration is. So
Oh,
it's
yeah.
kind of the match of the reality in the model and how well the model does to parameterize it.
Yes. That's legit.
Yeah, I'm always curious when people choose one.
Yeah.
Was it NSC, the codes that you used? NSC, right?
Well,
It was the NSC. code
Yes.
you used. Is that like a percentage of like predictive power, basically, of your model?
it's like a coefficient for seeing the accuracy of prediction.
Okay, yeah, because your first one was like a lot more accurate than your second one, like the river that you choose, is that like because of the amount of data that you used, or like, do you know why they were so different?
I have thought about why a lot, and that's the thing. I think the first one works much better. Is that because Rum River Watershed has a much higher flow, and Rum River has it was fed by the Lake Miloc, and it was compared to Rum River Watershed, Wild Rice River Watershed was a much slower watershed, and the stream flow was actually mainly dominated by the surface flow. And that is why I assume that that's why I share this slide, because I thought that it might be the reason why the surface storage can improve the prediction at a local level better at the Wild Rice River watershed. And that's my speculation. I might find out something new, but that's my answer by now. Does that make sense?
And I'll just mention that NSE is used commonly.
Okay.
Comparing predictions to zero. And Victor goes from 0 to 1, actually goes from minus infinity to 1. Minus infinity is really bad. If it's 0, you're better off just taking the average of the observed data for the prediction.
Okay.
Which is not very, you know, says the model's not any good.
Yeah.
And then if it's 1, of course, it's perfect. So it's like R squared. Exactly.
Yeah, that's what
Very
I
much
was.
like
Yeah.
R squared,
Similar.
but it's not exactly the same.
When it's like below 0, that means that it didn't have any merit. Yeah.
So what's the temporal frequency for the GRACE satellite that you used?
I didn't use GRACE satellite for this
You
experiment.
didn't.
Not in the future, maybe, but not now.
So how did you get your storage values?
I got a storage value and the stream flow both from the HSPF. Like at this stage of experiment, I will use the HSPF for the both for the. Sorry for confusion. I will just go back to that slide. I'll just go back. I got stuck a lot. Here. Yeah. So I got a storage, and since this is only the testing for I was only testing by including storage, we can improve the prediction. I want to see whether LSTM can learn it. So the water storage was actually not from the GRACE data. It was simulated by the HSPF. So it simulated the.
I mean, it seems to me that that's kind of cheating.
Oh, no, I mean, LSM doesn't know anything about the physics.
But you're using the model that you're
Oh, of course. yeah.
comparing your machine learning against to sort of give you a different way of evaluating the accuracy. So yeah, it'd be really interesting to see Grace and how that performs, or some other method which in fact may just relate to satellite estimates of soil moisture.
Oh, yeah.
Soil moisture might be a better surrogate than, you know, something that's really kind of, I don't know what the temporal frequency of Grace is anyway. That's my first question was,
Actually, the Grace is, I think,
it's finished, isn't it?
Yeah.
It's not,
No, they have a new one.
yeah, that Grace RO,
Grace two.
yeah.
Grace
Grace
follow-up. they
follow
call
up,
it.
yeah, FO, yeah.
Was put up in 2018,
oh, okay,
so, yeah. The first one lasted longer than they thought it would. And then they put up the second one. Now it's got a little higher resolution.
right, okay.
I'm a little confused about what the actual resolution, I thought it was 28 days, but I think it's a lot smaller, a lot more. frequent than that.
I think it's monthly. Monthly
Wow.
and, yeah, the Grace
I think
is
it's
monthly.
more often.
And, yeah, and spatial was like 300 kilometers, 300 kilometers, I guess.
So I mean, and we have done tests,
Right,
you know, on a large scale with Grace with these Huckay watershed. Doing just simple water balance, you know, we have a evaporation from satellite, and we tried different evaporation methods. And this one method that's put out by the USGS and by NOAA seemed to do really well against any correlation. Yeah. And then, of course, precipitation grid that we had. And so we do these water balances and the outflow, and we compare that to the total water stored from Grace, and they really follow each other nicely. You know, then the question is, well, you know, which layer should we use? Should, you know, can I use the total water storage, should we use surface storage, interception storage, and so on. So maybe you wouldn't use Grace. Maybe you just say, all right, I just need an observation well here at one location, because everywhere in the watershed, the level of that well should be somewhat related to what it is elsewhere. So you may not even need to use something like Grace. And maybe soil moisture, like you said, at a few places, we know that there are spatial correlation between values, right? So you may not have to outfit the entire watershed with these sensors.
do you have any observations on snowmelt runoff as a sort of different process than the runoff you get during the non-frozen period? I mean, it seems like in the Rice River watershed, you're gonna have a lot more maybe spring snowmelt
Yeah.
driven events, and in the Rum, you're not gonna have as much.
That is my current speculation, because when I reviewed the HSPF model, what they did is that they will include the snowmelt will be included in like in the surface storage. So they'll include that will be included in this as part of the service storage. So yeah, I assume that that's why it already include the snowmelt in it. But if I want to double check how much influence there are with snowmelt, I definitely have to probably do like independent test. I can't just tell you like immediately right now, like, oh yes, snow melt will determine its flow. But I think that is very possibly because it was already included in as a part of the surface storage here.
I think you know, maybe doing a good prediction during the non-snow season, right? And not as good during the snow season because of that snow storage. So that would be an important thing to account for it.
Oh yeah, I think maybe I should take a look at like more like season by season too. I think that might help me answer the answer. Yeah.
I do want to mention that John Lee, one of your colleagues, the WRS student, is close to finishing his PhD. And he has taught now twice in the spring semester of 2020 and 2021 a short course hours, basically 3 2-hour periods just small workshop using machine learning and environmental sciences. So I'm ready to encourage him to do it again this spring. So I mean, he has a lot of experience, took several computer science courses in his as a minor in WRS, and works closely with the computer science students still. So I think that if you're interested in that, it doesn't cost anything. You know, basically WRS pays for you to be able to, or for him to teach this class. And, so he teaches you how to, use the software. I mean, to develop software, use the software that you might be doing artificial neural network or some other kind of thing like that.
All right. Thank you very much.
I have to start sharing.
Thank you.
I am really interested in that.
Being a statistic, I mean, this is just statistics. Basically.
I really like learning like new programs. So,